Welcome back, folks. This is Mr. Johnson with you. We are in section 2.6, Equilibrium Problems, page 163 of our textbook, or 171 of the ebook. This is the last section of chapter 2, so we're going to be wrapping up our conversation about equilibrium by learning how to solve 3 different types of problems using skills and concepts we've acquired along the way. All right, here's the warm-up at the top of this page that I strongly recommend you try yourself. It guides you through how to fill in this table. Give it a shot, come on back, and see how your work compares to mine. Again, try this warm-up here at the top of this page. Come on back when you're done. All right, first thing I'm going to talk you through is how to think about and use this table. It's called an ice diagram or an ice table, which is the most common tool to solve equilibrium problems. I stands for initial. It represents the initial concentrations that are present in the equilibrium system. Sometimes there won't be a substance that has an initial concentration at all. Sometimes it might be 0. In this case, the product has an initial concentration of 0. C stands for change. That's the change that the substances undergo as they reach equilibrium. And then E stands for equilibrium. All right, so in the first question, it says to solve for the concentration of N2 at equilibrium. Well, if it starts at 3 molar and goes down by 2 molar, it'll end up at 1 molar. So I'm going to put a 1 in there for N2 for E. So now we want to find the changes that chlorine and NCl2 undergo. As the step reminds us, that changes will adhere to the stoichiometric ratios. The ratios of the changes will be the coefficients. If N went down by 2, and there's 3 chlorines that react for every 1 N, then chlorine should go down at 3 times the rate of nitrogen. If nitrogen goes down by 2, and chlorine goes down by 3 times that much, it should go down by 6. If one reactant goes down, the other one always goes down as well. So this is going to decrease by 6.0. If the reactants go down, the products always go up. The converse or reverse is true as well. If NCl3 goes up by twice the rate that N goes down, there's a 2 in front of NCl3, there's a 1 in front of N2, then NCl3 should go up by twice 2. It should go up by 2 times 2, which is 4, so positive 4.0. Notice I put signs in there to be really clear about whether they are going down or up. Again, if the reactants go down, the products go up, and if the products were to have gone down, the reactants would have gone up. This 2 to 6 to 4 ratio is the same as a 1 to 3 to 2 ratio. All right, if we know that there was no product to begin with and it went up by 4 molar, then at equilibrium, it will be a 4.0 molar. All right. So now we're solving for the equilibrium concentration of chlorine using the Keq value, the Keq expression that's equal to, and we'll plug in the values of N2 and NCl3 at equilibrium and solve for the equilibrium concentration of chlorine. First thing I've done is written the general Keq expression. It's going to be NCl3 squared, has a coefficient of 2 in front of it, over the 2 reactants, N2 and Cl2. N2 is raised to the first with no coefficient. Cl2, of course, raised to the third with a coefficient of 3. Now I've plugged in the Keq that exists for this system, 0.128, and I've set that equal to these values in the equilibrium expression. NCl3 is 4, so I've got 4 squared there. N2 is just 1, and then I'm going to say that the equilibrium concentration of chlorine is X, and that'll be cubed. I ultimately want to find the initial. So if the equilibrium is X and it's going down by 6, then the initial would be X plus 6, because the initial added to the change, right, X plus 6 minus 6 will give us the equilibrium concentration of X. So now we need to solve for X. So I got X cubed. When I did my algebra, it would equal 4 squared over 0.128. That is equal to 125. If I take the cube root of both sides, X equals 5. So the equilibrium concentration of chlorine is 5. And if it went down by 6, that means it had to have started at 11. So the initial concentration of chlorine, which is what we're ultimately solving for, is going to be 11. All right, so we're going to use all of those skills and concepts in 3 different types of problems. Sit back, relax, and enjoy this hopefully not too bumpy ride. First thing we'll do is talk about how we solve these problems in general, the concepts that underlie them, and then I'll walk you through the 3 different types of problems we'll learn how to solve. I'll do one with you and then give you a practice problem to solve on your own and to come back and compare to my solution. In equilibrium problems, I'm looking at this section in green here, it reminds us there's 3 variables or 3 values that come into play for an equilibrium system. There's the equilibrium constant, which could either be given to us or we find. There are the initial concentrations, which could either be given to us or we will find. And there are the equilibrium concentrations, which we will either be given or will find. There's also the C row, but that just tends to solve itself, and we'll talk about why. So ultimately, in these problems, we will either be given the equilibrium constant and the initial concentrations, and we'll be asked to find the equilibrium concentrations. Or we'll be given initial and equilibrium concentrations, and we can find the equilibrium constant. Or we could be given the equilibrium constant and the equilibrium concentrations, then we want to find the initial. So typically we'll be given 2 of the 3 variables that are highlighted in green, and we solve for the third. All right, so the first type of problem we're going to solve, looking at the section in blue here, is to determine Keq from initial concentrations and 1 or more equilibrium concentrations. If we were given all the equilibrium concentrations, that wouldn't be very hard. We just plug them into the Keq expression. So usually you're given all the initial concentrations and just 1, but not all of the equilibrium concentrations. All right, so I'm going to flip my book to solve a problem with you, and then we'll give you a chance to try one on your own. So I've flipped the page. I'm looking at sample problem 261 here on page 172 of the ebook. And I'm going to jump to my whiteboard and solve this for you. Of course, if you ever want to come back to your book and see how it was solved here, you should see that it aligns with my explanation, but sometimes it's nice to see or hear a solution more than once, or 2 different ways. So we're going to use an ICE table again for this problem. In fact, all of these problems should be solved using an ICE table. And it really doesn't matter if you keep track which type of problem it is. Rather, you just fill in all of the ICE table you can, you figure out which variables you do and don't have, and you then solve for the variable that's asked for in the problem. So let's give that a shot. First thing I do is I set an ICE table with as many columns as there are substances in the reaction. And then I write the reaction above that ICE table, each substance corresponding to a column. Meanwhile, if any of these were solids or liquids, we would eliminate them from the Keq expression, and they wouldn't get a column, or we just cross it out. And I'll show you what that looks like in a bit. But these are all gases, so they will show up in our Keq expression, and each of these substances needs its own column. All right, so I'm going to start to fill in everything in this table I can, and then, of course, leave blank what I can't figure out at first. We've got 7 moles of NH3. That's the reactant. There's only one reactant in a 0.5 liter flask. It doesn't mention about any product being present initially, so we assume those values to be 0 if they're not mentioned. I'm going to put in zeros for those. But remember, these represent concentrations. Keq is about concentration, so I've got to divide 7 moles by half a liter to get its molarity. Moles over volume being molarity. And 7 divided by 0.5 is 14 molar. So that's the initial concentration of NH3. And again, there's no product initially because they're not mentioned. At equilibrium, the concentration of N2 is found to be 6.2 molar. So I'll fill that into the equilibrium row for N2. It's given to us. All right, so now it becomes a bit of a puzzle. We fill in everything else in this table we can, based on what we learned in the warm-up. How that C row corresponds to the coefficients, or the ratio of the values in the C row does. Well, if N2 starts out at 0 and it ends up at 6.2, it had to have gone up by 6.2. So there's a gain of a 6.2 molarity of N2. Well, once we have one value for the C row, we can always fill in all the other values because, again, they correspond ratio-wise to the coefficients. Well, if N2 goes up by 6.2 and 3 times the H2 is produced for N2, then H2 is going to be 3 times 6.2. It's going to be 18.6. And that means that if it also started at 0 and it went up by 18.6, then at equilibrium it will have a concentration of 18.6 molar. Meanwhile, NH3 is consumed at twice the rate that N2 is produced. If N2 goes up by 6.2 and NH3 goes down by twice that amount, then NH3 will go down by 12.4 molar because 6.2 times 2 is 12.4. Again, if the product is going up, the reactant's going down. That's why those signs are the way they are. So if we know that NH3 started at 14 molar and went down by 12.4, it'll end up with a molarity of 1.6 molar. Next thing I do is write the general form of my Keq expression, ideally first without plugging in values. Keq will equal the products, H2 raised to their coefficients, 3 for H2 times N2 raised to nothing, over the reactant or reactants, in this case NH3 raised to its coefficient 2. So I'm now going to plug these values in. H2 at equilibrium is 18.6. That's cubed. N2 is 6.2. And NH3 is 1.6. And that's squared. I go to my calculator, and I get 1.6 times 10 to the minus 4 is the Keq value. And that, of course, is what the problem was asking us for. All right, so we're going to flip our page to 165 of our textbook. And I'm going to ask you to solve a practice problem. Come back and see how your solution compares to mine. So here we are, back to the book. Flip my page. It's practice problem 3. In orange, I'd like you to solve. And notice this ICE table has, as we talked about, a row for every substance. But in this case, the row for carbon has been crossed out because it's a solid. It won't show up in the Keq expression, therefore we need not contemplate it in the ICE table. So give this one a shot, come back, see how your solution compares to mine. Like the note says, even though carbon doesn't show up in the Keq expression, or we will provide values for it in this table, we are using the information about carbon to figure out the molarity by which O2 went down. If we started with 6 grams of carbon and it ended up at 1.2 grams, we know that 4.8 grams was consumed. We need to turn that mass into a molarity. So I divide the mass by the molar mass, and I get 0.40 moles of carbon consumed. Since this was happening in a 1 liter flask, then there's a decrease of a 0.4 molar. Meanwhile, if oxygen has a 1 in front of it and carbon has a 2 in front of it, then we know that the decrease of oxygen is half that of carbon. So if carbon goes down by 0.4 molar, oxygen's going down by 0.2 molar, and if it started out at 1.4, we know it will end up at 1.2, and I should put a negative there. Meanwhile, if carbon monoxide has a 2 in front of it and oxygen has a 1, that means CO goes up by twice the amount that O2 went down by. Twice times 0.2 is 0.4, and it's positive. And like we said, if nothing's mentioned about a product being present initially, then we assume it to be 0. So we put a 0 there, and if it went up by 0.4, it ends up at 0.4 at equilibrium. So now we just need to write the general Keq expression for this and plug in the values for carbon monoxide and oxygen gas and see what we get. Keq will be carbon monoxide squared, coefficient of 2 over oxygen. Again, eliminating carbon as it's a solid from the Keq expression. That'll give us 0.4 squared over 1.2, which is 0.13. Keq for this system is 0.13. So I'm on the same page. I've scrolled down. I'm now looking at the section here in yellow titled Determining Equilibrium Concentrations from Keq and the Initial. So this is the second type of problem where we're given Keq and the initial concentrations, and through an ICE table we will find the equilibrium concentrations. I've flipped my page. I'm now on 166 of my textbook, 174 of my ebook. Same thing. I'll do a sample problem with you and give you a practice problem to try on your own and to compare your answer to mine. So same thing as last time. We're going to set up an ICE table first for this system, giving each of the substances its own row and writing the reaction above so we can keep track of what's what. Notice these are all gases. None of them are solids or liquids, so they will all have a column and they will all show up in the Keq expression. All right. The following gases are injected in a 1 liter flask, 1.2 moles of H2. So we divide moles by volume. 1.2 over 1 is going to be an initial concentration of 1.2 molar for H2. HF is the same. 1.2 over 1 is a 1.2 molar initial concentration for F2. And again, if no product is mentioned initially, we assume it to be 0. So we're going to put in a 0 there. That note is important. When gases are combined, there's no dilution effect because the container is typically rigid and there won't be a dilution factor. That isn't the case for solutions, where when two solutions are combined, you have to account for the new volume and therefore adjust the molarity of each of those substances that was combined. So that's all we're given, just initial concentrations. If you're only given initial concentrations and no equilibrium concentrations, which means you can't put an actual value into the C row, then we use X's, and that's the case this time. If we start with only reactant and no product, the system can only shift to the right. The reactants can only go down and the products can only go up. So I'm going to say that H2 goes down by X, and F2 with the same coefficient of H2 also goes down by X. And since there's a 2 in front of HF, it will go up by twice the amount that H2 and F2 go down. So this is going to be plus 2X, which means that equilibrium, H2 will be 1.2 minus X, F2 will also be 1.2 minus X, and HF will just be 2X, because 0 plus 2X is 2X. So now I write my general equilibrium expression without values in it yet, and then I'll plug into that expression these values in the E row, equilibrium row, find X, and then figure out what I'm asked for in the problem to make sure that if it's not X, I'm providing the right value. All right, so Keq is going to equal HF in brackets squared, because it's got a coefficient of 2 in front of it. F2, no coefficient, no exponent, H2 as well. All right, now I'm going to plug in these values and set them equal to the equilibrium value I was given, which is 2.5. So I've got 2.5 equaling 2x squared over 1.2 minus x squared. The reason I did that is that F2 and H2 are both 1.2 minus x. So I put that in parentheses and said, all right, it's just 1.2 minus x squared. And the reason I did that, put 1.2 minus x in parentheses squared, is it makes this a little bit easier to solve. The numerator is squared, and so is the denominator. 2x squared over 1.2 minus x squared. So if I take the square root of both sides, that will take away the exponents from the right, and of course, I end up with the square root of 2.5 on the left. So that gave me 1.58, that's the square root of 2.5, and then of course those exponents disappeared on the right, and that's 2x over 1.2 minus x. Multiplied both sides by 1.2 minus x, and got this. Distributed 1.58 into both terms, and got this row here. Combined like terms, moved 1.58x over here, added them together, and I got 1.896 equals 3.58x. Divided both sides by 3.58, and I got x equaling 0.53, which may not be what the problem was asking. That may not be our final answer. So we got to go back to the question and see what it was asking for. And if you recollect, it's what will the concentration of HF be, the product at equilibrium? Well, we know that that's 2x, and if x was 0.53, I'm looking at this bit in blue over here, and we double it, we will get HF's concentration at equilibrium, which is 1.06 molar. Beautiful problem, full of great concepts, all sorts of great algebra. We'll try a practice problem here for you to take a look at on your own. So I'm now on 168 of the textbook, 176 of the ebook, looking at practice problem 262 here, highlighted in pinky purple. This is the one I'd like you to try on your own. Solve this in your book. Come on back and see how your solution compares to mine. First thing I did is took the 4.5 moles of HCl, the reactant that's in a 3-liter flask, and converted it to molarity. Moles over liters is molarity, 4.5 over 3 is 1.5. There's no mention of any product initially, so I set those equal to 0. And if all I have are initial concentrations, I have to use x's for my C row. Instead of going minus x for the HCl, I went minus 2x, so the other ones could be plus x. Just makes it a little bit easier algebraically to solve. But I could have had minus x in here, and plus 1/2, and plus 1/2. But I didn't. That means that HCl at equilibrium will be 1.5 minus 2x, and both H2 and Cl2 will be x at equilibrium, as 0 plus x is x for both. I've written my general Keq expression, which is chlorine times hydrogen over HCl squared. I then have plugged in the values for chlorine and hydrogen into that Keq expression. They are both x, so that's why this numerator became x squared, and HCl is 1.5 minus 2x, which squared is 1.5 minus 2x in parentheses, of course, squared. As both the numerator and denominator again this time are squared, I can take the square root of both sides. That makes this quite a bit easier to solve, giving me 0.6 on the left. The square root of 0.36 is 0.6. And getting rid of those exponents on the right-hand side. So I've just got x and 1.5 minus 2x off to the right. And through several algebraic steps, which I haven't shown, I found x to be 0.41 molarity. Now it's asking for how many moles of chlorine there will be in the end, not what the concentration will be. To go from molarity to moles, because molarity is moles over volume, we need to multiply by the volume. So this 0.41 molarity times 3.00 liters will give us the number of moles at equilibrium, which is 1.2 moles. And there's our final answer. Nice work, folks. All right, I flipped the page. I'm on 169 of the textbook, 177 of the ebook, looking at the section in green titled Determining Initial Concentrations from Keq and Equilibrium Concentrations. This is the third and final type of problem we will learn how to solve. Again, I'll do the sample problem with you and then give you a practice problem to try on your own. So we're looking at sample problem 263 here on this same page, and I'll jump to my whiteboard and solve this problem with you. All right, some CH3OH, methanol, was injected into a flask where it established equilibrium with carbon monoxide at a concentration of 0.15. So that's the equilibrium concentration. What was the initial concentration of methanol? So we've got the reaction here, and we've got Keq given to us. Again, it doesn't really matter in advance to know what of the three types of problems this is. Rather, build an ice table, fill in everything we can, and figure out the unknown variable. So let's give that a go. Here's the ice table. All right, there she is, and all of these substances should get a column. Nothing will be crossed out because none of them are pure liquids or solids. Next thing I'll do is fill in the information I have. Looks like carbon monoxide again at equilibrium has a concentration of 0.15 molar, so I'll put that here. I'm solving for the initial concentration of CH3OH, so I'll put an X in there. And again, unless I'm told otherwise, there's no initial concentration of product, so I'll put zeros in there. If we have an initial and equilibrium concentration for any one substance, then we can fill in the entire C row. If carbon monoxide starts out at 0 and ends up at 0.15, we know it had to have increased by 0.15. If H2 increases at twice the rate that CO does, it will go up by twice 0.15, 0.30, and end up as well at 0.30. Didn't need to say plus there. That's what it is. And then if CH3OH has the same coefficient as does carbon monoxide, it'll go down by the same value that carbon monoxide goes up, negative 0.15, and at equilibrium we'll get X minus 0.154 methanol. Once our ice table is filled in fully, which it is now, we write the generic version of the equilibrium expression and then plug in the values from the E row into that expression. So I'll do that now. So we've got Keq equals the concentration of hydrogen squared with the coefficient of 2 times the concentration of carbon monoxide over the concentration of methanol. Now I'm going to plug values into that. So I plugged in 0.040 for Keq because that was given to me, 0.3 for hydrogen squared, 0.15 for carbon monoxide, and methanol again is X minus 0.15. So now we just need to do some algebra and solve for X. First thing I did is multiplied both sides by X minus 0.15, which got it out of the denominator on the right and moved it to the numerator on the left. And then I squared 0.3, multiplied by 0.15, and I'm left with this expression here. I'm going to divide both sides by 0.04, add 0.15 to both sides, and when I do that, I get X equaling 0.49 molar. And that is our final answer because X in our ice table was the initial concentration of methanol, and that's what's being asked for. 0.49. Once again, fabulous job, folks. All right, last problem. Thanks for hanging in there with me today. Practice problem 263 on 178 of the ebook or 170 your textbook. Give this one a shot again on your own. Notice that we want to eliminate from the Keq expression NiS and NiO because they're pure solids. Come on back when you're done and see how your solution compares to mine. All right, let's take a look first at how I filled in my ice table. I know I'm solving for the initial concentration of oxygen, so I've set that equal to X. And it tells me that 0.36 moles of SO2 were found in the flask at equilibrium. Meanwhile, it's a 2-liter flask, so 0.36 divided by 2 is the concentration here of SO2 at equilibrium. If we know it started at 0 and it ended up at 0.18, it had to have gone up by 0.18. And if the ratio between O2 and SO2 is 3 to 2, 3 over 2 times 0.18 is 0.27, and that goes down because it's a reactant, which means at equilibrium, concentration of O2 is X minus 0.27. Here's my Keq expression, SO2 squared over O2 cubed. I then plug in my Keq that was given to me at 0.3, the equilibrium concentration of SO2 of 0.18, and the denominator, of course, is O2, which is cubed, X minus 0.27 cubed. Then I get into some algebra. I move X minus 0.27 cubed up to the numerator on the left-hand side, 0.3 to the denominator on the right-hand side. All of this, 0.18 squared over 0.3 is 0.108. But the left-hand side was cubed, so I cube rooted both sides to get X minus 0.27 on the left, and the cube root of 0.108 is 0.48. To finish this off, I've added 0.27 to both sides and found the initial concentration of O2 to be 0.75 molar. Congratulations on all the problem solving you've done today and for having watched the last lecture in our equilibrium unit, unit 2 of our textbook. Have a great day, folks. Be good to yourself and those around you. Look forward to seeing you in the next lecture.